This is Lab 5, and I'm Jacob Tommy. So for Lab 5, the experiment involves dropping a bar magnet down a tinfoil tube, and we are creating a computational model to calculate the magnetic force on the magnet and comparing the time it takes for the magnet to fall through the tube with the computational results against our experimental values. The first checkpoint asks why we can't use a ferrous material like iron or steel, and this would not work because then the magnet would simply stick to the walls of the tube and not slide down. So we need the aluminum tube, which is a conductive material, but it itself does not function as a bar magnet. For conducting the experiment, I found an average time of 1.92 seconds that it took for the bar magnet to fall through the tube. And the second checkpoint asks us to consider what happens and the magnet falls more slowly than it would normally without the tube. For the initial conditions, my tube of tinfoil was 12 inches long, or 0.3048 meters, with a width of 1 centimeter, thickness of aluminum foil. The inner radius was 0.01587 meters, and mu for the bar magnet was calculated in the last lab, and I got a value of 2.53. So that is what I used for the computational model. Next, we set up the function for the magnetic field, and this is the formula I used. This is the same formula that was used in lab 3. So this function returns the magnetic field when you input a magnet, a position vector. Next, we have to find the rate of change of magnetic flux. So here we use this derived formula, and where mu is the value that we had previously gotten from the third lab, y is the vertical distance between the magnet and an arbitrary loop in the tinfoil. V is the velocity of the magnet, which depends on the total net force that is exerted on the magnet, which we will find later on. So that value is calculated much later on and then used in this formula. And then the radius of the loop, which is constant, and here in the code is what this formula looks like. Then we have to calculate the current in the ring. Now that we have the flux, we can find the voltage, or the nth, and we can use that value to calculate the current by dividing it by the resistance of the aluminum foil. And so I is simply nth divided by resistance. Next, we want to calculate the force the magnet exerts on each ring. And we can do that using this equation. And the distance, or the position vector r, is going to be, the y component is going to be the distance between the bar and the ring. And then we're going to add the ring's radius as an x component to find that total r position vector. And then we just plug those values straight into this formula to calculate the force that the magnet has on each ring. And then in order to find the force that each ring has on the magnet, because that's really the force we want, we simply use Newton's third law and find that it's the same force, the sign is just switched. Next, we have to find the net force on the magnet. So we're going to add all the forces that are exerting on the magnet, which is the magnetic force, which we just found, and the gravitational force, which is simply going to be the mass times the acceleration of gravity going in the negative y direction. So when we add those two forces up, we're going to get the net force. Now we have the net force, we can use that to calculate the acceleration and find equations for the velocity and the position of the magnet as it falls. So our velocity equation is going to be v initial plus acceleration times delta t, and acceleration is going to be force divided by mass, net force. And our position is going to be position final equals position initial plus v final times delta t. And this is what it looks like in the code. And so every time it loops through, it's going to update with the new final velocity. And so we're going to get an accurate position coordinate. For my results, this is what my simulation looked like, and this is what my graph looked like. So initially, the velocity falls very quickly, and then it increases a little bit, but it's still negative, so it's still falling through the tube. And that's pretty constant throughout, and then it drops. So it increases speed at the very end. The result was 5.561 seconds, which when you compare to my values I found experimentally is much greater because my average value was 1.92 seconds. So there's a big discrepancy there. And the only thing I could think of was that I'd incorrectly calculated my mu value. So if you reduce the mu value from 2.53 to 1.5, that's a lot closer to what we see in real life. So maybe in actuality, the value of mu for this magnet is closer to 1.5. These are some hypothetical questions that the lab asks us to consider. If the resistance in the aluminum was close to 0, then the current in the tube would be very great, approaching infinity. And such a large current would then cause the force to be very great. And so what we would see is either the magnet would be prevented from falling all the way through and would just get stuck in the tube, or it would just hover above the tube without actually falling any distance. The second hypothetical question is if there were holes cut into the tube, there would still be a magnetic force on the bar magnet, so it would still fall more slowly. But since there was less metal, there's less free electrons and less current. So the force would be less than if there were no holes cut in.